Twice this week, I was asked, Mrs. Riggs, do we have a Regents exam this year? Twice this week, I wanted to cause physical harm to a student. No, I'm just kidding. Just may have wanted to punch him in the nose for that statement. Yeah, I guess you're right. So yes, in case it has not been made really clear this year to you, there is a Regents for this class, hence the reason it's called Regents Earth Science on your schedule. I just want to make sure you guys kind of know what you're getting yourselves into over the next few weeks. So yeah, we do only have 38 class days left. We are just about done with this chapter. The next chapter is only like a week, maybe a week and a half. The astronomy unit is a little bit longer, but we'll get through it no problem with plenty of time to review this year. Just so you also know, there is only, hang on, let me just check for officially. After you finish the lab you're doing now, which is the weather patterns lab, there are only 2 more real labs left. Yeah. Kim, remember when I was talking about punching people in the nose? Yeah, this is it, knuckle sandwich time. That does not mean you will have free time in lab. In fact, there won't be free time in lab pretty much the rest of the year. Because, sorry, you might get them done and then have the remainder of them for free, but not a whole period. Because we will be doing some reviewing in lab as well as in class. So the Regents this year is 2 parts. One part is what we call the lab practical. It is a lab Regents. So I don't know if any of you guys took the 8th grade science test, but if you did take the 8th grade science test, and if you remember, part of that was like a hands-on portion. I don't remember all of it, but I know one of it, there was a ruler that you had to roll something down the ruler, it hit something and you had to measure, had something to do with energy. This is kind of like that, where you take some of the stuff we learned in lab and class, and you get tested on it in a separate time from the actual test. This will be given to the lab part, is given during your lab period. It is only going to take 27 minutes to do the whole entire lab portion of the test. What it is, it'll be 3 very mini labs. Now, when I say mini, nothing like the labs we do in class where there's like readings and different sections. It's like a lab that's this big. Like there's nothing that much to do. In fact, it's so short, you were only given 9 minutes per lab. I'll tell you right now, I know that sounds scary to give a time limit, especially less than 10 minutes. I promise you, as long as you read the directions and do what the directions say, that's more than enough time. Most people finish by the 7-minute mark. For some labs and some people, they finish at the 5-minute mark. So it's not overly complicated, and we will be reviewing in lab for it. Basically what the lab final will be on is anything that you needed stuff to do the lab, like not just your reference table and the paper. So for example, rocks and minerals, you really can't do rocks and minerals without the rock in front of you. So that is always one that's on there. Like if the sling psychrometer ones where you got to spin stuff around, you can't do that without that. I've never seen that as an option because the sling psychrometers are so junky. I don't think they'll test us on that one. The density one where you had to actually weigh and measure stuff, that's totally an option. Oh, another one is the circle drawing, because I don't give you a regular compass on the actual test. That's fair game for the lab practical. So they are, like I said, just 9-minute mini tiny labs. That'll be worth 16 points of your actual Regents grade that you get. So it's not like you get 1 grade on the lab and 1 grade on the written part. They get combined. Speaking of the written part, this is the one from just this January that anybody had to take if anybody needed to do a makeup. This is what that looks like. So it looks just like what you guys probably are used to with Regents exams. It's just a test booklet. You get through, and every test question you've had this year has been a Regents question. So the format of the test shouldn't be a surprise to you. Like, there you go. we got just, which two weather symbols represent severe weather. You'll look these up. It's right off your reference table. It's nothing overly complicated. So for this, there are 50 multiple choice. And then the remaining 35 are what they call short answer. And sometimes short answers are literally one word. Sometimes it's a couple words. Sometimes if you go through, one of these is probably a graph. You answer them on a separate answer booklet. So they'll give you the separate answer booklet to do the short answer. Like if you need to do a map, my guess is this one had you plotting things on a map using latitude and longitude. It's right there. So it's actually kind of hard to skip questions. Like during my test, some people just randomly skip questions. It's almost impossible to skip one of these because you would have a giant blaring blank in front of you. So I don't think you'll end up skipping one. This test, by the way, the written portion is on Thursday, June 20th. It's in the morning. And there's no other test that day unless you're taking chemistry. Then you would have that in the afternoon, but I don't think any of you are also in chemistry. I think I know that. Does anybody have any questions about the Regents coming up? Yeah, Nick. So there is a curve, and I can't blatantly say the curve is add 5 points or add 10 points because it's different every year, but I can show you how it worked for this last exam. So hang on one second. York State Earth Science. Hang on, let me kind of give you an explanation. So to be honest, I don't fully understand curves. It's a math thing. It's a statistics thing. I took a class in college. Can't tell you I remember much about curves and how they officially work. And I don't even know if this is officially a curve. But how it works is we get this chart, which if you look, it kind of reminds you, hopefully, of the dew point and relative humidity charts. On the left side, is your written exam. So you can see it goes up to 85 points. It goes down to 0. So that's how many of the written questions you get right. And along the top is the lab portion. So it goes from 16 to 0 at the other end. And just like we do with the dew point and relative humidity charts, we take what you get on the lab part, what you get on the written part, bring your fingers together, and that's what it is. So for example, the only way to earn a 100 is to truly get a 100, to get 0 questions wrong. But you can see you can get 99s in a couple different ways by missing more than just one question. Most people are more concerned with what do you have to get to pass. I know some of you are in that boat, and that's fine. To pass, to get a 65. It's way down here. So Mr. Meek and I usually go by, remember there are 3 labs. So if you get 1 point wrong on each one, so it's 1, 2, 3, you'd be here at a 13. So to get that 65, if you get 1 wrong on each of the labs, to get a 65, you only have to get 39 out of 85 correct. And by the way, that is a 46 in real life. So to pass, if you only get 1 wrong on each one, you need to get a 46 on the rest of the test. Nick, are you even listening after you ask the question? So in that case, I mean, a 46 isn't that hard. Most of you have gotten above a 46 on every single test you've taken. So passing, while I'm not going to say it's a guarantee, is not as hard as you think. That was this January's test. This June test might be a slightly different scale. They kind of make the scale after they give the test to see kind of like which questions people blew and maybe the questions were bad, so they curve it a little more, things like that. Yeah.
Did they ever curve it down?
No, they'll never get a lower grade. So everybody will always get a higher grade than they earned, unless of course you got that 100 and then you just get the 100. Any other questions about the regions, whether it's the written part or the lab part? I'm not sure if I mentioned yet, the lab part will be given during your lab period for the most part. Some people who have testing accommodations, and again, if that's you, you know who you are. Mr. Juskevich will make up a, schedule for that. It'll most likely be like the first week of June. Mr. Mead and I have to sit down and officially schedule it, but it'll be during your lab period. And unless you get testing accommodations, you will not miss any other classes, just your lab, that's all. Okay, when it gets closer to the lab part, I will remind you the importance of being here and on time, but I'll tell you right now, since it is a timed test, if you show up late, you missed it. So it's something that you need to be in class for, which will be a struggle for some of my first period lab people. The rest of you probably won't have as hard a time, but my first period lab people, that one day you need to make sure you're here on time. Okay, any questions? All right, let's do it then. Let's get back to finishing up this chapter. So we will be, I think I said page 13, but I think we're done with page 13, right? Oh, do those 3 questions. Should have told you to do those already. Go ahead and do those 3 questions on page 13, the review of stuff we've already talked about. Take attendance. All right, looking like most people are done. All right, so it asks you to do these 3 questions. The first one is asking you which graph represents the relationship between the angle of intensity and the representing the angle of insulation and the intensity of insulation. Okay, there's just a blank there. The x-axis is the angle of insulation. Can you guys please point where the sun would be if it was a 0 angle? Okay, so again, those of you come with back to class with me. So I asked, can you point to where the sun would be if it had a 0 angle? Okay, a 0 angle is straight out. So whether you're pointing that way or that way, as long as you're pointing straight out. When the sun is there, so really close to the ground, low angle, is the sun going to be strong or weak when it's close to the ground? What? Weak. Okay, that would be like sunrise. So at like sunrise or sunset, is it like the hottest time of the day? It's usually the coolest. There are times when weather fronts pass through in the middle of the day, but that's besides the point. When the sun is low in the sky, like at the ground, it's not super strong. Now point to where the sun would be if it got up to 90. Straight up. So if the sun is straight overhead, how's that feel to you? Hot, strong, burning. If the sun was directly overhead, you could only be out for a little bit of time before you burnt to a crisp. Even those of you who tan easily and very rarely burn, If the sun was directly overhead and you were wearing no sun protection, you would burn. It's hot, it's strong. Which graph shows that when it's on the ground, it's weak, and when it's overhead, it's strong? Please show me an answer on your fingers. I am seeing the right answer. It is answer 3. When it's close to the ground, 0, it's very weak intensity. When it's straight above, it's a higher intensity. And if we were in the middle, it would have a middle intensity or a medium intensity. All right, question number 2. In the end, it says the air temperature rose slightly faster in Florida than in New York State because Florida. So what did you say? Why is Florida rising temperature faster? Everybody participate, please. We got it. Oh, everybody who's participating has number 2 up. Okay. Florida has a higher angle of insolation than New York. Hey, by the way, why does Florida have a higher angle of insolation? Closer to the equator. Good. And finally, question number 3 for review. The average temperature of the North Pole is colder than the average temperature of the equator because the equator, why is the equator warmer then? All right, I'm seeing a couple different answers. So it is saying the North Pole is colder than the temperature of the equator because the equator. We're looking for answers about the equator, not about the North Pole. So does anybody want to redo their answers then? Yeah, it is answer 3. The equator receives more intense insolation. I did see a few people answer number 1. Couple things wrong with number 1. The less would be for the North Pole, for one thing. And then continuing on, ultraviolet. Ultraviolet does not control the temperature. So you could be getting the most intense ultraviolet and you might not feel, or you wouldn't feel it because ultraviolet light has no heat. We need all of the insolation or just the infrared to get the heat. So when this specifically said ultraviolet, that should have been crossed right off because ultraviolet does not control the temperature. All right, let's move on. So we've covered angle of insolation, duration of insolation. The third thing that controls how much radiation we receive from the sun is basically what we call atmosphere transparency. So this is on page 14 in your packet. When I say transparency, what are you thinking? Clear, see-through. So transparency is saying how see-through it is. What are some things that will make the atmosphere more or less see-through? Clouds. So today we look out the window and you once again are seeing nothing but stupid clouds. Guys, I'm starting to get bitter. I am not one of those people who usually complains about the weather nonstop, but I am this year. This weather is making me mad. But anyway, I can't calm down, Nick. It's gross out there. It was nice yesterday afternoon. I did enjoy that. Whoa, I didn't hear what you said, but 2 people just told you to be quiet, so I'm gonna go with them. All right, guys, how much energy from the sun is getting down to earth today? Not much. If we wanted to go get a suntan out there today, well, it ain't happening, just like every other day this year so far.
Okay.
Nick, I'm gonna call your mom again. What I'm about to show you is going to be the basics of what happens to energy when it comes through the sky. I will tell you there are numbers associated with what you're gonna write down. Let me tell you right now, you do not have to memorize the numbers. So don't get hung up on the numbers. I'm giving them to you just almost for the shock factor, I guess. So we've got all the sunlight leaving the sun, all those radiation waves, all the insolation leaves the sun, but most of it doesn't get here. And here's what happens. So at the top of this, so you guys have this exact picture in your notes. Okay, why is this not moving? There we go. At the top, I want you to say there's 100% incoming solar radiation. So at the top of our atmosphere, There's 100% being shot at us. Right off the bat, the clouds are gonna do some work. One thing the clouds do is they reflect. Do you guys know what reflects means? Returns, it bounces back up. So already almost a quarter of the sunlight gets bounced off the clouds and back into space. Another 25% gets stuck in the clouds, so gets absorbed. That is absolutely why sometimes the clouds look bright.
Same thing with.
Exactly, yes. So the clouds are doing their job. They already block out or prevent about half of the energy from even reaching Earth. But once that energy reaches Earth, some of it doesn't even stay here. So some of it hits the Earth's surface and is bounced back out into space. So that's 8% is reflected by the Earth's surface. And then that remains just under half, 43% gets absorbed into the Earth.
Wait, hold on. Depends on what the sun radiation.
Oh, yeah. You ever, does the sunlight ever seem brighter to you on some days than other days?
No.
No?
Well,
That's one. Sean, what are you thinking? Especially when there's what on the ground? Snow. Think of snow. You ever been outside when it's been?
Oh, yeah, I've been like flashbang, but
Okay, so when it's those bright, sunny, but cold days, when the sun is shining, but the snow is still there, you need sunglasses. You need sunglasses because not only is the sun shining down on you, but it's hitting the snow and reflecting back into your eyes. Where some other times when this same idea happens? Not just snow will reflect a lot of light. Sand can reflect a lot of light. What else?
I was gonna say, cause snow and sand are like.
Okay, what else is light colored? Okay, how about even a cement driveway versus a blacktop driveway? That cement will reflect some of the light. How about lakes, oceans? When you're out boating on a really nice summer day, that water will reflect the light back into your eyes. So again, the moral of the story, please do not at all even focus in on the numbers. The key is that the clouds block out or prevent half the light from getting to us, and then a little less than half gets stuck into the Earth. Now, what we're going to do is talk about exactly what Colton was already talking about. Let's talk about how much gets reflected or absorbed. I should have asked you this already, but Colton already brought it up. What do the lakes and the water or lakes and the snow and the sand have in common? They're all light colored objects. What are some dark surfaces that you can think of? Blacktop. How does blacktop feel on a bright sunny day? Hot. Blacktop compared to cement. How does the cement feel? Blacktop absorbs it and the blacktop becomes uber hot. The cement isn't as warm. I'm not saying it's cold, but it's not as warm. Why would the cement be not as warm? Because it's reflecting more. So underneath these pictures, so dark surfaces, like Sean said, absorb the greatest amount of heat. That's the first bullet. Dark surfaces absorb the greatest amount of heat. Now that second bullet, and then light surfaces, let's go over there, they reflect the greatest amount. The second bullet on each is one we haven't talked about. once the sun stops shining, how does the blacktop feel? Is it still warm a little bit at night? And then eventually it gets really cool. Things that are good absorbers are what we say are they're good radiators. So they radiate the same amount of heat. Blacktop can absorb it. Blacktop will also give off the heat. Whereas because the light colored surfaces, because they weren't absorbing the heat as easily, they will not radiate the heat as easily. And this is also true for rough and smooth surfaces. Rough surfaces, they have more surface area to absorb heat. So rough surfaces are going to absorb heat more. Smooth surfaces are going to reflect heat. And a rough surface, I'll let you finish writing and then we'll talk. So rough surfaces don't have to feel like sandpaper rough. They just have to be not perfectly smooth. Can you think of some rough surfaces that might absorb heat better? Gravel driveways. They will absorb more than the same material. So if I don't know what his gravel is made out of, but if his gravel was made out of limestone, which is probably an option, it could be. But if we took like a cement block and broke it up into pieces, and then compared the pieces compared to the smooth block, the pieces would absorb more energy because there's more surface area. What are some other things that absorb heat really well, even if they're light colored? But because they're rough, they absorb good heat. You ever been to a beach on a bright sunny day? How do your feet feel on that sand? Hot, but most of the sands that you've probably been to, unless you've been to like Hawaii where they have the black beaches, most of the sand that you've probably been to is light colored. Why does the beach heat up even though it's light? Because there's more surface area. Every single piece of sand, if you were to look at it under a microscope, would be more than likely a bunch of squares. And because those squares are piled up, gazillions of them, they have so much surface area for the heat to absorb. It's even true about sweaters or sweatshirts compared to t-shirts. What are some of the characteristics of sweaters? They got ridges in them. You can feel the individual like bumps where the yarn is put together. Even your sweatshirt, think of the insides of your sweatshirt. What are they made out of compared to a t-shirt? You got that fuzzy material. Those fuzzies are the same material as your t-shirt, but because they're not nice and smooth like a t-shirt, they're going to absorb the heat. So rough surfaces absorb more than smooth. And this goes to what we've already talked about, land versus water. Or your pool deck compared to the pool. Which one heats up faster in the morning? Pool deck heats up faster. What's one reason? Take a look at it. It's dark and rough. Dark and rough is going to absorb the heat and make it hotter. So these are the two bullets that go in land versus water, which is something we have already talked about. I'm gonna need you to put that away because we're not focused. Thank you. So we talked about this when we did land versus sea breeze a couple weeks ago. I don't think we used the actual term specific heat, and I know we didn't use the reference table that goes with it, so we're gonna introduce that today. So land's always gonna heat up faster because it's a good absorber. But the problem with that is because it heats up fast, it's also going to cool down faster. How about, can you guys imagine making macaroni and cheese right now? The real, well, the kind that you need to do on the stove with a pot of boiling water. I really want to focus on the pot of boiling water. What heats up faster, the pan or the water? The pan heats up way faster. Which one would cool down faster, the pan or the water? The pan cools down way faster. The same concept, and that's called specific heat. Specific heat. So we got 2 more bullets and then we're done, or 2 more slides and we're done. This one and 1 more. It's the amount of heat. By the way, heat is measured in joules. So just like length is measured in miles, joules is just a unit. So it's the amount of heat needed to raise the temperature of 1 gram of substance 1 degree Celsius. And then when you're done writing this, grab your reference table, front cover. So the amount of heat needed to raise the temperature of 1 gram of substance 1 degree Celsius. Guys, in other words, this is just saying how much heat do you have to add to something to heat it up? You guys just told me the pool deck required less energy to heat up than the water. It heats up faster. You told me the pan requires less energy to heat it up than the water does. It heats up faster. On the front page, on the front page of your reference table, top right, you have this reference table. So front page, top right. This is a list of, what is it, 2, 4, 6, 8, 9 things I think I counted. 9 common materials that they give you the actual specific heats off to the side. I'm going to tell you right now, the numbers themselves, again, are not super important. They're not going to make you do math or anything. The key is that when you have a bigger number, it means it requires more heat to heat it up. Like water, that pan and the water, you told me the water requires more heat. It heats up slower. Now, pans are typically made out of some sort of metal. You'll notice here at the bottom of the page, there are 3 different types of metals. Look how much smaller these numbers are. They require less energy, just like you just told me. One little addition that I think you should make to this reference table is off to the side, I would say a column calls heats up, and at the top, at water is the slowest. And at the bottom at lead, it's the fastest. And that's actually the only labels I would add. So water heats up the slowest, lead heats up the fastest. Now there's a couple other things. We got solid water, which is ice, and water vapor, which is gas water. You can see that those heat up a little bit faster than liquid water. So the last slide you need here is the higher the specific heat, the more energy required to raise the temperature of the material. The lower the specific heat, the faster it heats up. We'll just do a couple of practice here and then we'll be done. No homework again tonight. See if you can answer those first four questions, A, B, C, and D. Which one heats up the fastest? Which one heats up the slowest? Which one well, you can read them. Just the first four. So on this chart, which one heats up the fastest? Lead. Lead heats up the fastest. It's got the smallest specific heat, which again means it requires the least amount of energy. Which one heats up the slowest? Liquid water. It's got the biggest specific heat. Question C, which one needs the most amount of energy to raise its temperature? Liquid water. It's got the biggest specific heat. That means it requires the most amount of energy. Which one? Oh, I didn't realize D was this. Okay. Here's the last thing I want you to do for the day. In each set, circle the one that would heat up the fastest. So I already did the first one. Out of water, iron, or copper, copper will heat up the fastest because out of those three, it's got the lowest specific heat. I know I said no homework, but I just make sure these circled ones are done before class tomorrow, which I think you are all done with those, but we'll go over these tomorrow. That's where we'll start off.